Another topic that we covered in the Weathering and Sedimentary Rocks learning module was the characteristics of sedimentary rocks and what those characteristics can tell the geologist about the sedimentary environment that existed when the sediments were deposited. So the different characteristics are listed here, and we'll try to quickly review some of the things about each of these different features or characteristics that we discussed in the learning module. That's going to be on the second test also. So composition refers to the mineral composition of the sedimentary rock. And just to give you an example of how that can sometimes tell the geologist something about the environment where the sediments were deposited, I'd refer to the limestones, which are dominated by calcite mineral in their mineral composition. And most limestones form in a relatively shallow marine setting. Usually the calcite material in the limestone rock was produced by marine organisms that secrete calcium carbonate mineral to make their hard parts. So, when a geologist sees limestone rock, the first thing they'd start to think about is maybe this area used to be a part of the ocean, a relatively shallow part of the ocean. And, kind of look at the rock characteristics in more detail from that. It's not to say that limestones can't form in freshwater environments, it's just that they much more commonly form in marine environments, in certain marine environments in particular. And then, the other chemical sedimentary rocks like dolostone and the evaporites. With the dolostone, we learned that dolostone forms from diagenetic replacement of an original limestone, so they're going to start thinking again about where do most limestones form when they see dolostone rock in an outcrop. And the evaporites, we said, things like rock gypsum, rock halite, they require a dry climate where you have water evaporating at high rates. Okay, so let's move to the next set of sedimentary rock characteristics, the texture of the sedimentary rock. And by texture, we can talk about things like the average size of the particles that make up the rock, or the average grain size. We could also think about things like sorting. Okay, that refers to the range of particle sizes that you see in the sediment deposit or sedimentary rock. And even things like the grain shape. That we discussed when we were reviewing the sedimentary rock classification, how the grain shape of the gravel-sized particles determines whether you call a rock conglomerate or breccia. Okay, so let's talk a little bit about the grain size. Remember that when we see coarser grain sizes, we think of high energy flow conditions, and we see finer grain sizes like mud, we think of lower energy conditions, deposition in very slow moving water or maybe still water, something like that. And so, right, we're talking about that, we're saying that the water is going to sort the sediments out by size. It's going to put the coarser grain sediments where the water is moving faster, and put the finer grain sediments where the water is moving slower. So if you want to think about an environment where conditions where you can get really poorly sorted sediment materials, you have to think about something like this along the margins of a melting glacier, where you have all different particle sizes frozen up in the glacial ice, and all that's happening along the margins of the melting ice is the sediments are just kind of, thawing out. Getting poorly sorted deposits like this requires deposition by something other than water, maybe melting ice or deposition in some kind of mud flow or rock flow or something like that. Okay, let's turn to the next item here, the sedimentary structures, and I think we only talked about maybe 3 of them in the learning module. Cross-bedding, and that's real common in the sandstone rocks, right? And it looks kind of like this, where you have the sedimentary rock layers, but within the layers you see these inclined cross beds. So, right, and we talked about in the learning module. We talked about how the cross-bedding forms from the migration of ripples and dunes. It could happen on the bottom of a river. Cross-bedding will form in shallow marine settings also as a result of wave action. And it can also form, of course, as a result of wind blowing over a sandy surface. We could get large sand dunes formed. So here's a picture of the Great Sand Dunes National Monument in south central Colorado. Sand dunes that will form in this kind of setting are going to be much, much taller than the ones that form in a river setting or on the seafloor. So the thickness of those cross-bedded layers is going to be much greater, maybe on the order of a few tens of feet thick. And that would allow the geologist to distinguish between cross-beds formed as a result of wind depositing the sand versus water deposition in a river or in a coastal setting. Planar lamination. With lamination meaning sediment layers that are really, really thin, only a millimeter or two thick. That's what we mean by lamination. Okay, the planar lamination, that can form in either really low energy settings. So if we saw the planar lamination in mud-sized sediments, right, we'd think, okay, kind of still water, maybe on the bottom of the deep part of a lake or deeper in the ocean, and the very, very fine-grained muddy materials can then settle out of the still water. And we also talked in the learning module about an example where the planar lamination will form in sands as a result of higher energy conditions, placed like on a beach face where the waves break and lap up and back on the swash face of the beach, or the beach face. You get the planar lamination in the sands there. And then the third sedimentary structure we talked about were the mud cracks. And you know, they're going to form in muddy sediments in locations where the mud periodically gets wet and then dries out. Okay, the bed geometry. And then if you step back from the outcrop and look at a outcrop, maybe in a road cut or something like that, you know, you might see that the beds aren't perfectly horizontal. Maybe they have some kind of inclination to them, something like this kind of bedding. So that's what we're talking about there. And in this photograph of a road cut from upstate New York, you can see those gently inclined layers. That kind of thing can form in a setting like on a river point bar. Okay, like this point bar is in the Brazos River, down here on the Texas coastal plain. And a point bar is a sandbar that forms along the inside of a river bend. And here at low flow you can see that sandbar. And it is very, very gently sloping toward the outside bank of the meander bend. So, right, when the sediments get deposited on a sloping surface like that, the layers themselves are going to have a tilt to them or be inclined. Going back to this picture, and the thing about it is it's sandstone, coarser grained sandstone at the bottom, and you know, when you it starts to get hard to see those inclined layers up here at the top and the rock's kind of rubbly. Well, this is mudstone up here, or shale. So lots of times we'll see within a set of sedimentary rock layers like this that some of these characteristics, like the grain size in this case, changes as you go vertically upward through the stack of sedimentary rock layers. And that's what we're referring to when we talk about the vertical associations. Okay, you look at the characteristics of the sedimentary rocks over a larger series of sedimentary rock layers, and the characteristics change as you go vertically upward. And that means that the conditions within the environment were changing through time. Our last characteristic are, you know, we could look at the fossil content of the sedimentary rock, and that's going to be very helpful. If our sedimentary rock has fossils in it, it's going to be very useful. See what kind of fossils are in the rock. We know that some kinds of critters like to live in some locations and not in others, so the fossil content is going to be a good indicator. of what kind of environment existed in the past.